So once again, we look for submatrices of the data matrix that have some specific pattern, some specific homogeneity, whatever, yeah, where the values follow some specific criterion, some specific pattern. And the patterns are defined here in this list, basically, or these are the different types of patterns. So the first one is the very simple one, constant biclusters. The second one, biclusters with constant values in rows and or columns, and then biclusters with coherent values, and also biclusters with coherent evolutions. And we will have a closer look at all of those four different general types, actually. And we'll start with the constant biclusters. So those are potentially the easiest model, or the most simplest model. In that case, all points have to share an identical value in selected attributes. Yeah? So this constant value called mu here is the prototype value, the typical value for the cluster. So the cluster model is pretty simple. All the values need to be identically. All the values need to have exactly the value mu. Yeah? And that is obviously a special case of an access parallel subspace cluster. We will see that on one of the next slides, why that is the case. Here, first of all, the example. So here, that is a data matrix of 4 rows and 3 columns. We will also always use this kind of example here with 4 or several columns and several rows here. And obviously, we have a cluster, a submatrix, which consists of the 4 rows P1 to P4 and the 2 columns A1 and A2. And all the values here have the same value. In that case, it's a 1, but it could be a 2 or a 3 or a 4.5 or whatever. Then this typical value, this exact value would be in all these values here, in all these cells here. Yeah? And the third column here obviously does not belong to this submatrix, because here the values are kind of arbitrary. Yeah? And if you look at the spatial pattern, yeah, so how does this matrix pattern correspond to a spatial pattern in the data space? Well, all the points here belong to a kind of access parallel subspace cluster. So along the irrelevant attribute, which is A3, obviously, the points spread arbitrarily. Yeah? But in the relevant attributes, A1 and A2, in the relevant features, in the relevant columns, they have all the same value, meaning that they are all on the same point when we project all the data points on A1, A2. Yeah? So if we project all those points only onto these 2 columns, A1 and A2, obviously we have 1, 1, 1, 1, 1, 1, 1, 1. So all of those points are actually identical. Yeah? And that is regardless whether this one is 1, the typical value mu is 1 as here, or the typical value mu is 0.5, then everything is 0.5. Yeah? So the interpretation is, the spatial interpretation that is important is that the points are located on the bisecting line of the participating attributes. Yeah? The participating attributes are A1 and A2. So this is the submatrix actually of this one here, which is the bicluster, the constant bicluster. Yeah? And all the points are basically on one specific point. And this specific point is located on the bisecting line of A1 and A2. Why is that the case? Because, well, it's always 1, 1 or 2, 2 or 5.5, 5.5. So it's always on one of these points here on this bisecting line here. Yeah? So that's why that's a special case of a subspace or projected cluster, because it is a kind of dense or super similar set of points here. So even if you allow a little bit of bias here, a little bit of jitter, even if it need not to be exactly the same, then it would be very, very close together somewhere here. But it cannot be somewhere arbitrarily on this A1, A2 plane, yeah, but it must be here on the bisecting line here. That's why it's a kind of special case of what we actually already know with subspace or projected clusterings. Yeah? So that is the spatial interpretation of constant biclusters. We will also use a visualization technique which is called parallel coordinates in order to see what kind of patterns are actually in these biclusters. Yeah. So the parallel coordinate visualization is very tricky. So on the x-axis we have the attributes. Yeah. So here you see A1, A2, A3, and on the y-axis we just have the values, the actual values in the corresponding features. Yeah. So for the green one we have 1, 1 in A2 and then 0.2 in A3. For the black one, P4, we have also 1, 1, so it should be, of course, identical here for all these 4 points here. So each observation now is a kind of graph here, yeah, because each observation has in each attribute, of course, some specific value, yeah, and we just record that here, or we just draw or record here these values graphically and draw a line in between. Yeah, so this one here, this line here, or this line segments actually are P3. This graph here is P4. This one is P2, and this here obviously is P1, because P1 here we have 3.5 here in A3 here. Yeah, so that is parallel coordinates, which is a nice visualization tool. It's a kind of scientific discipline to visualize points and patterns using parallel coordinates, because the order of the attributes are actually very, very important. But that's a different story. We don't want to go into details here. But if you find it interesting, you can do a lot of things visually with parallel coordinates, because this is a nice visualization tool also for arbitrarily for data with any dimensionality, obviously. Yeah, so so the dimensionality is just another line or record along the x-axis. So you always have a kind of two-dimensional visualization of a d-dimensional space. Yeah, so that is the nice thing with parallel coordinates. Anyway, so we want to see what kind of patterns do we see when we look at the parallel coordinates if we have constant biclusters. And you see here that we have the line here should be, of course, überdecken, of course. Yeah, so they should completely overlap here, because all the red and the blue and the black and the green ones, they have 1 in both A1 and A2. So the graphs should be identical here. And then if it comes down to the non-relevant attributes, which is A3 here, the graphs actually split up in different directions. Yeah, so that is the basic visualization. So if you see something like this in your parallel coordinates, you can already say, okay, this is a constant bicluster pattern, which can even be identified visually by parallel coordinates. Okay, so that is the basic idea. Once again, constant biclusters, we have in this submatrix a constant value in all rows and column pairs, and that is spatially a special case of subspace clustering.